Okay, so a quick chit chat about the difference between sigma bonds and pi bonds. And so a sigma bond is forming directly along the bonding axis. So if we define the direction of the bonding axis as the x Cartesian axis, why didn't I do an arrow? I don't even know. Let's do an arrow instead. That would be easier. An arrow. So this is my x-axis, like so, and this would be my y-axis, and then my z-axis is going like through the plane of I guess the screen, right? So x, y, y, and z, like that. Okay, so I've got like some sp or sp2 hybrid orbitals, whatever, they got the same shape, right? And they are going to be overlapping in a linear fashion, which means, okay, imagine we've got two nuclei. I'm just going to do some nuclei in different colors, right? Nucleus 1, nucleus 2, something like that. Back to my drawing thing, and then some kind of ugly oh, it's green, whatever, sp hybrid orbital. So the overlap is occurring directly between the two nuclei. So this is where my electrons is at, right? So this is what we call a sigma bond. So that has the Greek symbol sigma, which is kind of like a little sideways 6. Okay, so sigma bond is a linear overlap of electrons between the nuclei forming a bond, forming a bond. All bonds have a sigma bond. So a single bond is just one sigma bond. A double bond is one sigma bond plus one of the other type of bonds, which is a pi bond, and that is what we call lateral, or side by side if you prefer, overlap of electrons. And that is either above and below the bond, or in front and behind the bond. So I'll show you what I mean. Okay, so pi bonds actually form from like unhybridized p orbitals. So where's my thing that I want? This one. So if we imagine we had like a py this way, hang on, let's draw it actually over the nucleus. So my py is above and below the nucleus that's forming the bond, and so is this one. I'm sorry, it's kind of ugly, but you know. So the overlap of electrons is going to be occurring sort of here and here. So not actually where the bond is being formed. So that is one double bond being formed, okay? The PZ would be like in front and behind that, so it's really hard for me to draw on a two-dimensional surface, but I'm sure you kind of get the idea, okay? So just to be clear, a sigma bond, single bond even, a single bond is one sigma, okay? A double bond is one sigma plus one pi, because you have to have overlap between the nuclei, otherwise you're not forming a bond, right? So that's your sigma, and then the pi is like bonus bonding, which is from the unhybridized p orbitals above and below the plane when the bond's being made. A triple bond has double bonus, okay? So you have one sigma bond that's forming like the actual bond between the nuclei, and then you've got one pi above and below that bonding axis, and a second pi in front and behind. So that's coming from overlap of like the py and the pz, unhybridized. And the single pi bond is coming from, I don't know, let's just call it the py, just to be fun. I'm sorry, I guess statistically it could be either unhybridized. Unhybridized. There we go. Writing. Okay, so if we're asked about this particular highlighted atom, which is this carbon right here, it says how many sigma bonds does this atom participate in? So one way I teach this is to just go ahead and label the sigma bonds. Like if you've got a big molecule in particular, just kind of go and like say, hey, 1, 2, 3, and like tick them off. Like, because if you've got a really big molecule, you don't want to like, you know, get to 59 and lose count, let's say. So there's 3 sigma bonds. Okay, and then how many pi bonds? So like get a different color if you want. And I see in this double bond is 1 sigma plus 1 pi. So that's this one here. So there's only 1 pi bond. What is the orbital hybridization? Goes straight back to the steric number. Okay, so we have 3 bonds and no lone pair, so the steric number is 3. So that is telling me that it's going to be sp2 hybridized. Okay, so those hybrid schemes have to match up with the numbers, right? So 1s plus 2p 1 plus 2 gives me 3. And that also makes sense because that carbon is able to form a double bond. So if you look at our table for sp2 hybridization, you're going to have one leftover p orbital, and that is going to be able to then go ahead and form that double bond because it forms a pi bond as well as the sigma bond. Okay.